In section 2 of chapter 1, we're going to be reviewing the real number system. First thing we'll do is learn how to classify real numbers according to the different subsets of the real number system. From there, we're going to look at some different properties of real numbers and then utilize those properties to simplify variable expressions. Okay. All right, so the real number system. Every number that you've ever worked with in mathematics before has probably been considered a real number, okay, or classified as a real number. The real number system itself is typically designated with a capital letter R. Sometimes it's written as like a fancy script R, okay? But within the real number system, there are, let's think of them as smaller subsets, okay? The first subset is the natural numbers, or sometimes referred to as the counting numbers. And these are going to be designated with a capital letter N, and they would include the numbers of 1, 2, 3, 4, 5, and so on. When you first began to count, you probably began with the number 1, moved on to 2, 3, 4, etc. Second subset of the real number system are the whole numbers, designated with a W, capital letter W. And the whole numbers are going to be all of the naturals as well as the number 0. Okay, you can't have the concept of a whole without having the concept of 0. So notice that all natural numbers are whole numbers, right? All natural numbers are whole numbers, and every whole number is considered a natural number as well, with the exception of 0. The next subset would be the integers. The integers are represented with capital letter Z. We'll see why here in a moment. And integers are all of our whole numbers as well as their negatives. So that's telling me that all my natural numbers, all of my whole numbers are considered integers. If an integer is negative, it would not be a natural or a whole number. Okay. Next subset would be the rational numbers. Rational numbers are designated with a capital letter Q. That's because we've already used R to represent the entire real number system. Now, by definition, rational numbers are any number that can be written as a fraction or ratio of two integers. So you can't have the concept of a rational number without first understanding what the integers are, right? Once again, a rational number is any number that can be represented as a fraction of two integers. So let's give you a few examples here. All right. 1/2. 1 is an integer, 2 is an integer. 1 divided by 2 is a fraction of two integers. So it would be rational. -2/3. -2 is an integer, 3 is an integer. -2 divided by 3 is a fraction of two integers. All right. One final example, -5. Now, -5 in itself is an integer, and if you think of it as being over 1, then it's now represented as a fraction of two integers, right? So that's important because it shows us that all of our natural numbers, all of our whole numbers, all of our integers can be considered rational numbers when you think of them as being over 1, divided by 1. Okay? Now, there's an alternative way of looking at rational numbers from a decimal perspective. Okay, so let's take some of the numbers that are already here. 1/2, we know in decimal form, is 0.5, right, or 5/10. That's a terminating decimal. So any terminating decimal can be considered a rational number. It can be rewritten as a fraction of two integers. -2/3 we know is -0.6 repeating in decimal form. Any repeating decimal is considered rational because it could be rewritten as a fraction of two integers. Okay. Our last subset of the real number system is the irrational set of numbers. And this is why we couldn't use the letter I when we were designating the integers. It's because I has been set aside for the irrational numbers. Simply put, if you're not a rational number, you are an irrational number. So that means irrational numbers are any number that cannot be written as a fraction of two integers. It's the opposite of the definition of a rational number. The most famous irrational number probably is pi. Its decimal form doesn't terminate, doesn't repeat. Okay. Another common example would be the square root of 2. Really, the square root of any non-perfect square. So square root of 2, square root of 3, square root of 5, 6, so forth. Those are going to be irrational numbers. Their decimal forms would not terminate, would not repeat. All right, and then one more example here. I can have some fun with this. About 1.01, 011, 0111. All right, notice there's a pattern to the decimals of this number. However, it's not a terminating or repeating pattern. Therefore, it would be considered an irrational number. Okay? So there is a hierarchy to the real number system, right? And I can represent that with a tree diagram. Once again, all numbers that you have worked with thus far, first and foremost, can be considered real numbers. But from there, you can get more specific as to what kind of a number it is. So it's either going to be rational or irrational. Now, if it's irrational, it's kind of an oddball. It's off on its own. It couldn't then be classified as anything further, right? But rational numbers can be broken down into more specific subsets. So if a number is rational, as long as its denominator is 1, then it's also an integer. Okay? And if it's an integer and it's positive or 0, then we know it's also a whole number. And if it's a whole number, chances are it's probably also natural unless it was the number 0. All right, so once again, understand how the tree diagram works. All numbers are real numbers. They can then be more specifically classified as rational or irrational. If they're irrational, they're the oddballs. They're by themselves. If they're rational and have a denominator of 1, then that means they are integers as well. If they are integers that are positive values, then they are whole numbers. And if they are a whole number other than 0, they are also natural. All right, so here we have 4 different numbers. We'd like to classify the sets of numbers to which each belong. All right, the square root of 6, that's a real number, right? It exists, but its decimal form would be non-terminating and non-repeating, making it irrational. If it's irrational, can't be classified any further than that. Okay? The next number of 5, we know that's a real number, and it can be thought of as 5 over 1, right? 5 itself is an integer, 1 is an integer, so that's a fraction of two integers. That means we're working with a rational number. And being that the rational number is over 1, it's also an integer. Being that it's a positive value, it's also a whole number. And being that it's a whole number other than 0 makes it a natural number as well. Negative 43. That's a real number. Think of it as over 1. That's a fraction of two integers. That means it's a rational number. And because the denominator is 1, that means we're working with an integer itself. But since the number is negative, it cannot be whole, it cannot be natural. Okay. Last example is 2/3. That's a real number. 2 is an integer, 3 is an integer, so 2/3 is a fraction of two integers. That means we're dealing with a rational number. Notice the denominator of this rational number is 3, not 1. Therefore, it could not be classified further into an integer, a whole, or a natural. All right, moving forward. All real numbers, no matter what type of real number they are, there are several properties that apply to different operations performed on those real numbers. So we're going to run through those properties here. I'm going to use the letters A, B, and C within these properties to represent any real number. Okay, so we'll start with the commutative property of addition and the commutative property of multiplication. Let's start with addition. If I'm adding together A plus B, that's no different than B plus A. So it's telling us we can add in any order. The result shouldn't matter. 1 plus 2 is the same as 2 plus 1. This works for multiplication as well. A times B is equal to B times A. Right? 2 times 3 is the same as 3 times 2. Notice the commutative property does not apply to the operations of subtraction and division, right? A minus B would not result in the same thing as B minus A always. Same thing for division. Right? The associative property of addition requires the use of 3 letters. Let's say we want to add 3 numbers together. If I want to do A plus B plus C, I have to add 2 numbers together at a time. So I'm going to throw some grouping symbols in here. B plus C would be added together first. The sum of that then gets added with A, right? Well, it would be no different than if I added A with B first, then took the result and added it with C. Okay? Notice the order in which I wrote A, B, and C on either side of the equal sign didn't change. From left to right, it's A, B, and C. What changed is where I placed my grouping symbols. Okay? The same would work for multiplication. If I want to do A times B times C, I can multiply B and C together first, then take the result and multiply it by A. Or I could multiply A and B together first, multiply the result then by C. Should get the same result. Okay. All right, from there we have the additive and multiplicative identity properties. So basically this is just stating in terms of addition that if you take any real number, A, and you add it with 0, you're gonna result in the same number that you started with, right? So a plus 0 equals a, and the number 0 is referred to as the additive identity. That's the one number that can be added to any other real number and not change the value of that real number. In terms of multiplication, this property would be a times 1 equals a. Okay. And the number 1 here is known as the multiplicative identity. Okay. Next set of properties are the additive and multiplicative inverse properties. If I take a and I add it with its negative, what's the result going to be? 0. So a and negative a are referred to as additive inverses of one another. Notice what it's resulting in, 0, which is the additive identity from above. In terms of multiplication, a times 1 over a equals 1. A and its reciprocal, 1 over a, are considered multiplicative inverses that result in a product of 1, the multiplicative identity. All right, and our last property, I'm sure you're very familiar with, the distributive property. If I'm taking a number a and I want to multiply it by the sum of two numbers b and c, that would be equivalent to a multiplied by b plus a multiplied by c. So it's telling us here that if we're on the left side of the property, you're adding b and c together first, and then you're multiplying by a. Or you could multiply b by a first, c by a, then take the two results and add together. Okay. Distributive property is great for just multiplying large numbers together, right? So, for example, let's say I want to multiply 7 by the number 42. I'm going to think of that as 7 times 40 plus 2, right? Which would be 7 times 40 plus 7 times 2 by the distributive property. And those two multiplications are a little easier to do, right? 7 times 40, 280. 7 times 2 is 14. 280 plus 14, 294. So that's a great use of the distributive property. All right. Name the property illustrated by each equation here. So in the first one, part A, we have negative 8 plus 8. That's being simplified to 0. Negative 8 plus 8 equals 0. That is nothing more than our additive inverse property. Three plus 0 equals 3. So we're taking a number, we're adding it with 0 for it to result in itself. That's our additive identity property. Part C, 5 times 1/5 equals 1. A number times its reciprocal equals 1. That is the multiplicative inverse property. Okay. What number is the additive inverse of negative 2/3? So we're saying what number, when added to negative 2/3, results in 0? That would have to be positive 2/3. What number is the multiplicative inverse of negative 2/3? So what number, when multiplied by negative 2/3, equals 1? That would be its reciprocal, negative 3/2. Okay. All right, now last example here. The properties that we just discussed in the last couple sheets, these are properties that can be used to simplify algebraic expressions. Right? You've done this before, you probably just haven't thought of it in terms of properties. So we have a pretty complex expression here. We want to simplify this down as much as possible. I'll begin with my distributive property. 3 times 4x is 12x minus 6y, and then distribute negative 2 to 3x plus y. That's going to give you negative 6x minus 2y. Make sure you distribute the negative there. Let's label that as the distributive property. Okay. All right, now I am going to do a little bit of rearranging here. Okay, I'm going to take and group the terms that have x with them together and those that have y together. So let's make this 12x minus 6x followed by negative 6y minus 2y. And you may not have realized it there, but what you have just used is the commutative property of addition. Now you say, wait, nothing really is being added there, it's being subtracted. Well, what you can really think of subtraction is it's addition by a negative, right? So really we are adding here. Okay. Now I'm going to take 12x minus 6x and I'm going to treat that as 12 minus 6 times x, and then negative 6y minus 2y, I'm going to treat that as negative 6 minus 2 times y. And what I've done there is use the distributive property again, kind of in reverse. All right, now we simplify. 12 minus 6, that's going to give us 6 or 6x. And then negative 6 minus 2, that's going to give us negative 8 or negative 8y. And we are as simplified as we can.